The mysteries of the universe have always captivated researchers, and among them, the concepts of dark matter and dark energy hold a special place. These peculiar, almost fantastical ideas are firmly rooted in the modern cosmological model. While it might be tempting to dismiss them as pure fiction, it's impossible to ignore the undeniable fact: ordinary matter, composed of the familiar protons, neutrons, and electrons, alone cannot explain the full spectrum of gravitational effects observed by astronomers. To this day, scientists cannot do without including invisible forms of matter and energy in the universe's model. These enigmatic entities not only produce effects that perfectly align with observed phenomena but also shape the universe precisely as our most advanced theory of gravity describes it. However, the assumption that everything around us is built upon something invisible, which emits no energy, cannot be detected in laboratories, and has no discernible impact on the world except for gravitational attraction, though widely accepted, still prompts a search for alternative explanations. This is where it gets truly interesting, as one intriguing alternative hypothesis for dark energy has recently emerged, potentially overturning our understanding of the cosmos. First and foremost, it's necessary to delve into the foundational principle underlying all modern cosmology: our comprehensive understanding of the universe. Surprisingly, this principle was first formulated back in the 15th century. Nicholas Copernicus, a great thinker of his time, boldly declared that Earth does not occupy any special, privileged place in the universe. This assertion, which then seemed quite audacious and non-obvious, today causes no doubt and has even evolved into something far more expansive, what is now known as the cosmological principle. It states that regardless of where an observer is located in the boundless cosmos, they will always perceive the same large-scale structure. In other words, the universe is homogeneous, and this homogeneity will not change regardless of the direction one looks. It is isotropic. Today, with three-dimensional maps of galaxy distribution throughout the universe available to scientists, this characteristic seems highly plausible and logical. However, it's important to note that the idea of a homogeneous and isotropic universe initially arose merely as a specific assumption. This was necessary during a period when scientists were actively working on creating an effective model of the universe that could align with the revolutionary general theory of relativity. As is well known, according to Albert Einstein's brilliant idea, the geometry of spacetime directly depends on the distribution of matter and energy within it. But his equations proved to be nonlinear, and solving them in the general case was enormously complex. Therefore, to simplify the task, the outstanding mathematician and physicist Alexander Friedmann made a bold assumption: the universe is homogeneous and isotropic, meaning it is uniform and smooth in all directions. This step allowed him to successfully solve Einstein's equations and finally describe physically sound models of the universe fully consistent with the general theory of relativity. These are the models we know: the universe either expands or contracts, and its geometry can be open, closed, or flat. Indeed, these very models allowed for the prediction of the universe's expansion, which was subsequently brilliantly confirmed by Edwin Hubble. Later, other scientists found solutions to Einstein's equations that also corresponded to the expansion of space, and the Friedmann, Lemaitre, Robertson, Walker, FLRW, metric became the canonical mathematical description of standard cosmology. Over time, the capabilities of astronomical observations expanded significantly, and the uniform distribution of galaxies on large cosmic scales confirmed Friedmann's initial assumption. Finally, after the monumental discovery of the cosmic microwave background (CMB) radiation, the homogeneity and isotropy of the universe on the largest scales were definitively accepted as foundational and now serve as an unshakable cornerstone for modern cosmology. Notably, Big Bang cosmology has proven remarkably resilient. It has readily adapted to new, sometimes very strange discoveries, such as dark matter and, most critically, dark energy. In 1998, the entire scientific world was literally shocked by the results of distance measurements to Type I supernovae, which turned out to be significantly farther from us than the then-current understanding of the universe's expansion predicted. Cosmologists realized that approximately 5 billion years ago, the expansion of the universe began to accelerate, a truly mysterious and unexpected development, it must be admitted. Because it was known that the universe is flat, and the gravitational pull of all matter and energy should, on the contrary, have gradually slowed its expansion. Therefore, for the observed universe, which is clearly accelerating, to remain flat, it needed to be balanced by something. A new parameter was added to the equation, the cosmological constant, which, paradoxically, Einstein himself had once proposed. By adding this coefficient to the equation, cosmologists once again obtained a flat universe, but now one expanding with acceleration. Thus, we got dark energy, a mysterious phenomenon with a repulsive property, the nature of which no one still understands. Undoubtedly, such a turn of events cannot satisfy all scientists, and it is very tempting to seek alternative explanations. Some researchers attempt more precise measurements of supernova distances, hoping to find statistical errors in previous measurements. However, others conduct new analyses and constantly confirm the existence of accelerated expansion. There are proponents of revising the theory of gravity itself, allowing that its laws might be incomplete on cosmological scales. But there is yet another, very unconventional and intriguing way to get rid of dark energy, to abandon the idea of a homogeneous and isotropic universe. Yes, this may indeed sound a bit heretical, as the distribution of galaxies in three-dimensional space and especially the CMB map perfectly confirm the cosmological principle. But questions still remain about how much local inhomogeneities can be ignored, and it is precisely here that the key to solving one of the greatest mysteries of the universe may lie. It is known that slight temperature fluctuations in the cosmic microwave background directly reflect density fluctuations of matter in the early universe. These primordial inhomogeneities formed the basis and a kind of template for the subsequent distribution of matter, ultimately leading to the emergence of large-scale structure. The modern configuration of galaxies and their clusters was essentially imprinted in these ancient variations. During the expansion and evolution of cosmic space, a complex network gradually formed, consisting of regions with a higher concentration of matter, the so-called galaxy superclusters. Between these dense formations, on the contrary, lie colossal empty spaces, or voids, where the density of matter is significantly lower than the average. Although these regions are not entirely empty, they contain sparse gas and individual galaxies. Their scales are truly impressive. They can reach tens and hundreds of millions of light-years. Notably, voids larger than 160 million light-years can occupy up to 40% of the universe's total volume. If all smaller voids are added to this volume, together they constitute more than half of all observed cosmic space. Thus, despite the fact that at the very beginning of its history, matter in the universe was distributed almost uniformly, over time, gravity contributed to the formation of discrete structures, and the distribution of matter and energy became significantly more inhomogeneous. This phenomenon raises a very interesting question. How exactly do these observed inhomogeneities affect the universe's expansion process? The widely accepted modern cosmological model, known as lambda CDM, certainly acknowledges the existence of inhomogeneities in cosmic space, but it assumes that their impact on large-scale average expansion values is negligible. Nevertheless, there is an alternative concept, the inhomogeneous cosmology model, which proposes to account for this effect. The main idea is that gravitational influence will affect the expansion of space itself differently, depending on the observer's location, whether they are in a dense galaxy cluster or amidst a vast cosmic void. Within galaxy clusters, where the concentration of matter is extremely high, expansion occurs more slowly because, according to the general theory of relativity, the expansion rate directly depends on the mass of matter and energy. Consequently, in these dense regions, the curvature of space increases, slowing down the expansion rate. Conversely, in voids, where matter density is minimal, space expands faster. Since voids occupy a significant portion of the universe's volume, they can potentially influence the average expansion effect, thereby creating the impression of acceleration. In such a context, there is no need for any unknown form of energy. Accelerated expansion could simply be a consequence of the uneven distribution of matter in the universe. Remarkably, Such a model readily explains why the effect of accelerated expansion became noticeable in the universe only about 5 billion years ago. This moment, by the way, is another point of contention in standard cosmology, because the hypothetical inclusion of dark energy immediately after the Big Bang would have led to such a rapid dispersal of the universe that the formation of galaxies, and consequently the emergence of life on Earth, would have been impossible. However, within the framework of the inhomogeneous cosmology model, this poses no problem. 5 billion years ago is simply the moment when matter had sufficiently clumped together for voids to begin to dominate and significantly influence the overall expansion effect. Moreover, this model perhaps possesses an even more intriguing interpretation, based on one of the most paradoxical effects of general relativity, time dilation. This hypothesis is called timescale cosmology, and it was first proposed in 2007 by cosmologist David Wands. Reflecting on the phenomenon of the universe's accelerated expansion, the author suggested considering the effect of clocks that function differently depending on their location in space. According to the principles of relativity, different observers, both near and far from massive objects, perceive the passage of time differently. Consequently, within galaxy clusters, ideal clocks would run slower than in regions with low matter density, i.e., in voids. Thus, clocks located within the Milky Way would run significantly slower than identical clocks within a vast cosmic void. It follows that more time has passed in voids than in dense clusters, meaning the expansion of the universe in these regions has been more significant. Therefore, the average effect of the expansion rate observed throughout space creates the impression of acceleration, as voids occupy a dominant position. This certainly sounds intriguing. However, the question of evidence arises. David Wands, the originator of this idea, along with his team, conducted a series of tests of the hypothesis, measuring distances to supernovae and comparing their models' results with the widely accepted lambda-CDM model. Initial results were quite encouraging, as timescale cosmology seemed to fit observations as well as the standard model. Nevertheless, another group of scientists later refuted these findings by testing the alternative model on a significantly larger sample of supernovae. In response, proponents of the alternative hypothesis published new work disputing their critics' conclusions, pointing to possible errors in their calculations. Well, this is a classic story of scientific development. And despite all its elegance, timescale cosmology certainly has a number of significant drawbacks. It is somewhat more mathematically complex than lambda-CDM, as it introduces a new parameter, the fraction of voids in the universe. Furthermore, it is extremely difficult to model, demonstrating how inhomogeneities affect the average expansion requires extraordinarily complex simulations. And finally, proponents of this model will have to make considerable efforts to reconcile it with the cosmic microwave background map, which is very accurately described by the lambda-CDM model. For these reasons, due to its relative complexity and certain rawness, this model currently has only a limited number of adherents. Nevertheless, on December 19, 2024, a new scientific study was published in which proponents of the alternative hypothesis made another attempt to convincingly demonstrate the clear superiority of their model. This time, the team of authors conducted a thorough analysis of what is effectively the largest and most accurate set of observational data, known as Pantheon Plus. This extensive dataset encompasses over 1,600 recorded Type I supernova events, located across a wide range of redshifts, corresponding to various distances from our planet. A distinguishing feature of this dataset is the higher precision in measuring light curves and a significant minimization of systematic errors. The researchers decided to test the timescale model on such an extensive dataset for the first time and compare its results with the widely accepted lambda-CDM model. Their findings proved to be very intriguing. At relatively low redshifts, i.e., within the so-called local universe, timescale cosmology demonstrated a clear statistical advantage over lambda-CDM. This suggests that the influence of matter distribution in homogeneity, namely the presence of large-scale voids, may play a very significant role in explaining the observed expansion of the universe on small scales. When considering medium redshifts, scientists found that both models are statistically roughly equivalent and equally capable of successfully describing the expansion process. Finally, for higher redshifts, corresponding to larger cosmic scales where the universe appears more homogeneous, timescale still retains a small but noticeable advantage, at least as the authors assess their conclusions. It is worth noting that the researchers are cautious in their conclusions and emphasize that their results look very promising, but there is still a need for new, more precise data, especially for low redshifts, where the influence of matter inhomogeneity is most pronounced. Furthermore, the authors acknowledge that their model does not necessarily fully reflect the true nature of dark energy, but the main message of their work is that excessive adherence to a single theory can be detrimental to the advancement of science. Of course, each of the alternative hypotheses holds its alternative status precisely because it is largely inferior to the standard cosmological model, which is distinguished by its simplicity, clarity, and, as it seems, excellent agreement with observational data. The concept of dark energy, regardless of whether it is a cosmological constant or some exotic form of energy, constitutes an integral part of the lambda-CDM model, and therefore there is no doubt it remains the leading explanation for the phenomenon of the universe's accelerated expansion. However, it is precisely this aspect that represents the most vulnerable point in our current understanding of the cosmos. Many questions indeed arise concerning dark energy, and answers to them are catastrophically few so far. Particularly telling is the striking discrepancy between the theoretically predicted power of dark energy and what is actually observed. Quantum field theory, which describes dark energy as vacuum energy, calculates its value to be a colossal 10 to the power of 120 times greater than the actual observed value. If dark energy truly possessed such immense power, even atoms would be ripped apart by its influence. This is, without exaggeration, the greatest mismatch in history between theoretical predictions and empirical observations. It is evident that we are unequivocally missing something fundamental in our understanding of this mysterious substance.